It's not working here. Are you picking up? No. It's okay. So I still need to use this mic. Okay. Okay, so we have mapped our images, right? So all our images are being mapped into a tensor of images. We can take however number of images we want, and then we can plot them just to check that everything is working. The next thing we're going to be doing is to create the image and their labels and put them together into one single data set, right? So one way, I'll show you one way of doing it right now, and then later in the modeling workshop we'll have another way which I personally think is easier, but this is one way you can do it. So again, tf.data.dataset from tensor slicers. So this will now take in the labels. So first we have taken in the whole list of the image paths, and then we map them into the image tensors. Now what we're going to do is to take the labels, the list of labels, and then we will map them again into a label data set. So we have an image data set and our label data set, put them into a tuple, and then we can zip them together in a zip data set format. So we have a zip data set with our images that we have already resized and scaled, 160 by 160, 3-channel image, and our labels. So this is basically the pre-processing part of the images. So as long as you have a list of, if you start with a list of your folders and the list of your labels, you can zip them together into this tensor zip dataset format, and then you can pass them into a model, right? So just to show you that it works. So we have our image and label zip dataset. To pass them into a model, we want them to be well shuffled, right? And then we want to batch our datasets. So shuffle and batching is pretty straightforward again. So you can just take the dataset dot shuffle, okay, and then you can repeat, and then you can do your batching, right? So all these are made pretty straightforward. So first you shuffle, then you take the dataset, repeat, batch, and then here prefetch lets you prefetch the data, so it makes the computation much more efficient. So if we don't prefetch, then say the CPU is processing something, and then while you are transforming the data and loading, your GPU is idle, and then when your GPU is idle, your CPU is running something. When the CPU is idle, your GPU is running something. So you take a long time to do the processing. But if you prefetch, then everything is loaded beforehand. The idle time is reduced. The prefetch.
The repeat.
Repeat. The repeat, I actually don't use it when you see in my the modeling workshop later on. I'm not quite sure why the author of the notebook actually put it. Does anybody familiar with this functionality know what it's used for? No? Yeah, I mean, I guess I could look it up and maybe let you guys know. I don't really use it. So basically what shuffling and batching are the main things that we will be using, and that's actually sufficient for the transfer learning task. So now we have an image label dataset. You can do the shuffle and repeat actually steps with this one helper function. You don't need to do them separately, right? So actually you can do the same thing, image label dataset, shuffle, repeat. You can batch and prefetch them. Now to pipe the dataset into a model is pretty straightforward. So tf.keras.applications.mobilenet-v2, that's what we'll be going to be using for this the modeling workshop segment. So this is just a preview, and just to show you that you can load the model. This is what we're going to be using, so MobileNet v2, and then with this input shape, and so later on I'll be covering why you want to include top false and set this trainable to be false. So this data set will basically be passed into the model, and you can see, later when we go into the model workshop, you can see how actually the Eagle mode is really powerful for this purpose. You can just put the data set through the model, and then you can see how it transforms the shape of the data set. So any questions for the pre-processing so far? Yes?
With the last code, where did you put the data? Because I cannot see the...
Not yet, yes. Okay, so if you want to put in the data, so what you can do is, so let's say you have loaded data, right? So this is the model that you have. Let's say I call it base model. You can just pass the image batch into your model, and then so basically, so let's say I have a batch of size of 32. Again, you can just pass straight in, and then it tell you that basically your model will take in your image batch, and then so you have a 160 and 3-channel images, batches of 32. It get passed through the model, comes out, you have 32 batches, and then you have a 5x5 by 1280 tensor. So that's what the model does. So in Eagle mode, you can actually just put in your tensors and then output here. So I'll be talking about this actually during the modeling workshop. So any other questions for the transformation?
Does it matter if the data set is imbalanced and then you want to...
Yeah. So if the data set is imbalanced, right, then you will be learning. Basically, you will be learning more. For this workshop in the modeling, I'm only looking at accuracy, right? So we don't want to be. If it's imbalanced, then that will totally skew your metrics. Yeah. So I think it still matters. Yeah.
So it doesn't affect the repeat. The repeat just doubles or the data set.
If it's imbalanced, is it? Or
if you haven't registered, please go to the back and look for our operation team.
So yeah, if you haven't registered, please go register so that you can get your GCP account for this workshop. Yeah.
The GCP account is only valid for today only.
I think few days.
Your GCP account will last until about noon time on Monday. I'm not sure. I think it follows GTM, so London time zone.
Yeah, so you can after today you can still go home and play around with your workshop materials. Feel free to edit anything. So that's the pre-processing part. The next segment of the workshop is the classification of the images. Does anybody need a break before that? No? Okay, so we go straight into modeling. And anyway, the model will take some time to train, and then I think we can have coffee break while the model is training, right? So, okay, so to train our model, we'll be starting from this folder here, modeling workshop. So the notebooks are in modeling workshop, emotion model.ipython notebook. So our task is to do facial expression classification. So as you see just now, so I've covered one way that you can pre-process the data, right? We take the list of paths, list of labels, then we zip them together into the data set. So here I'm actually covering a slightly different way to do things, again using TF data. So the same things, you load up all the TensorFlow, in this case TensorFlow GPU in beta mode. So I have already the image zip files in the GitHub that you have already cloned. So we can unzip the files, and then again going through the same steps. Going through the same steps, we get the list of paths, all image paths, and so we want to put. So I'm putting basically all this into a function, get image paths. So making use of get image paths, I get all the list of image paths, right? So that's the same steps, and then just take a look at the first few once again. So neutral, fear. Yeah, I don't quite think that the labels are actually quite accurate. But again, the second image looks pretty happy to me, but it's labeled as neutral, right? But so, and then we have the label names. We map them into the integers, right? The integer labels, and then we read the image. We decode the image. So that's a transformation that we'll be doing, right? So now, so we put them into the functions, and then we use map. We'll be using map to decode, to pre-process all these images, right? So, so here I'm covering this is the part where it slightly differs. So instead of zipping the image and labels together, so what I'm going to be doing is to directly pass the tuple of paths. So it did in my helper function, so I directly pass my list of paths and labels as a tuple into the dataset from tensor slices. So you can just straight away pass this tuple into your dataset object. So and then I'm using my helper function to just split the dataset into a train dataset, validation dataset, and a test dataset. So then I'll use the map function to map all this into our images, image tensors, and then return the train, validation, and test sets. Right, so that's what I'm going to be doing. So I'll have a train, validation, and test dataset using the split, load, and preprocess from path label function. So you can pass in the split weights. In this case, we are using a 80%, 10%, 10% split. Now, so again, so let's take a few and inspect them. Looks fine to be and it's transformed correctly, right? And then, so here I do a shuffle and batching. So for the train batches, I do a .shuffle, .batch. For validation and test, I just batch them together. And then if you take one of the sample from train batch, so it's got it's a batch size of 32. Image is 160 by 160 and 3-channel image. So the next part, we'll be actually doing the transfer learning. So we want to pass the dataset object that we have through the model that we have. So has anybody done transfer learning before? So just to get a sense of what's the level. So who has not done transfer learning? Okay, most, I guess. So those who have not raised, not sure what you've done is transfer learning or not. Yeah, so this workshop is actually based on a Google, there's a Google Code Lab, and there are various exercises that you can find on Colab also on transfer learning, right? So I'm basing on one of the Colab notebooks, but I've modified that to use to do transfer learning on emotions, which we thought would be more interesting. So we are going to use MobileNet v2. Yes, sorry. Neil.
Sorry, who raised your hand?
Okay, so we are going to be using MobileNet v2. The reason is that it's really lightweight, and since it's a data-to-device workshop, MobileNet v2 has got to be the model that we're going to be using. So we want to train a lightweight model so that we can take the model and then pass on to save the model and go to devices and do prediction right on the devices itself. So we thought that'd be really cool. But I'm not sure if Sam talked about it just now. So there's a small problem with this. So the conversion from your save model to a TF Lite that you want to put on your device is not really working for TensorFlow 2 now. So, but since we want to do TensorFlow 2.0 and cover the latest ways to do things, then there's a compatibility issue. The save model that we will still be doing saving the model and converting to TF Lite, but the version as it is now cannot be used for the devices. So the conversion part is the quantization part is the part that has an issue at this moment. But we think that going forward, this will be the pipeline that will be they'll be using. So the conversion part hopefully will be fixed by the TensorFlow team soon, and then you can use this pipeline and then just train a model, convert it, and then put it to your put the quantized model onto your device and start serving predictions, right? Now to transfer learning. So what transfer learning does, for those of you who has not done it before, is basically taking a pre-trained model, in this case MobileNet v2, which is trained on a huge set of images. So, so in this case, it's trained on ImageNet. There are 1.4 million images of 1,000 different classes. So we have a huge model that's already been trained on this huge set. It's able to do classification to a pretty good accuracy on 1,000 different classes, right? And it's got a whole bunch of different like random categories like jackfruit, strange, cats, dogs, and so different things, trees, tools. So it's got a whole bunch of different random stuff, 1,000 different categories. And it it's able to do classification, object detection on these different things, right? Now we want to make use of this already pre-trained model, which means it's got a whole bunch of weights already being tuned and accustomed to doing classification, right? And then we take that model, we remove its classification layers, we add back on top a few more layers that we want to do our own custom classification. We train them on our own data set just to get it accustomed to the fine-tuned differences of the emotions, and then do the classification on our data set, right? So that's what transfer learning basically does. Take a pre-trained model, you got to freeze it so that you only train the few top layers that you added yourself. Right, so the first task is a basic classification task. We will take the base model, right, which is the MobileNet v2 model, and we will so include top equals to false here will basically remove the classification top of ImageNet. So we don't want to classify 1,000 different classes. We just want to tune it to our 7 different emotions, right? So we remove the top weights from ImageNet. So it's going to take some time to download your base model here, right? And now you can take your image batch you've already pre-processed in the steps before, pass it to the model, and then you can see that this is the output shape, right? So you have, this is your batch size, 5 by 5 and 1,280 different slices, right? So we set the model trainable to be false. So we want to extract, for transfer learning, we have to extract what we call embeddings, right? So since the model has already been trained on a large class of data set, then typically you think that the model has been tuned to visual images, right, to looking at things. Yes.
Error on 31.
31.
Actually, the last one, right? The previous step, many people are getting a resource exhausted error.
Okay. So you have a resource exhausted error. That's to do with the machine. So the VM that you have. So I get that sometimes too. I think so. If you just do because you've already ran a notebook before, so I think the resources are being already consumed. So you want to shut down your previous notebooks. So shut down every single notebook first. So if you want to shut down, you just right click on the notebook and then shut it down. So shut down this emotion model and shut down also the previous data preprocessing notebooks. And then when you restart your notebook, you should be able to run it. So I guess, yeah, because we already ran the preprocessing just now, so almost everybody should be getting this error. But this is, you can resolve that.
If you are new to the Tensorflow API, we strongly encourage you to run everything from start and try to read through. If you have any question, you can ask the mentors on site. If you're already familiar with the APIs, then that's probably fine. The next section is probably more interesting.
Okay, so to extract the embeddings, which is basically, so we have a whole set of features that the model has been trained on all these images. It recognizes, it changes all these images, transforms them into a lower dimensional representation, right, of the visual world, right? So this lower dimensional representation we call embeddings, right? So we take this, we freeze the model by setting trainable to be false, and then we want to use this base model to basically just as what we did, pass the images through the model and get for each image that every batch gets transformed into these embedded representations, right? So if we take a look at the model summary, you'll see that, okay, so the input layer is 160, 160, and 3 channel. That's what we transform our data into. The output, it's got a whole bunch of layers. And the output is a 5 by 5 by 1280 shape. So that's what you saw. And since we've frozen all the parameters, all 2 million of them, nothing is trainable at the moment. All this model does right now is to take in images and pass out the transformation. It does not change any weights, right? So, and then what we're going to do is to add on our own classification layers now. Since we've already removed the classification top, we want to add in a global pool, tf.keras.layers global average pooling 2D. So what this does, you can see it immediately, right? Just by creating this layer, you can immediately pass your feature batch through, and you can see what it does to your image batch. So it transforms your image batch into a 32. So it's batch 32 and 1280 shape, right? So basically we've compressed we've pulled all the 5 by 5 together into one single number, right? So since it's 5 by 5 by 1280, and then we pull all them together into just 1,280 features, right? So now if we take, again, we can, we are going to add in the final layer, which will do the classification. So what, after pooling, we have 1,280. We are going to add a dense layer with 7 outputs, since we have 7 different classes to predict. Then with a softmax activation. So now if we pass our feature batch average through this layer, you'll see that it just outputs our batch with the 7 different classes. So the final model is basically a frozen base model that just does the extracts and embeddings for us. And then these are the layers that are free for us to tune, to train, right? So so we need to compile the model in order to fit it. So we compile the model with a RMS prop optimizer, and then a sparse categorical cross entropy, since we have 7 different classes, and our output labels are integers instead of being one-hot encoded. So if you have one-hot encoded labels, then you can just use a categorical cross entropy. But if you have integer labels, you should use the sparse categorical version. And then if you look at a model summary, this is the frozen one. And then you have a pooling with no parameters. And your dense layer, which is 8,962 parameters that are trainable. So your model actually only has so this about 9,000 parameters to be trained on. So that's 1280 times 7 plus 7, right? So so these are so let's take a look at our. So I'm just going to calculate the number of samples that we have. So the training sample, validation, and test sample. And then let's look at the initial evaluation of the data. So let's say I pass in model.evaluate, I pass in validation batches. Initially, the accuracy is about 10%. And so we have about 10-11% accuracy. So we are going to feed the model. So we pass in the train batches with 10 epochs, right? And so this is our validation batches, and then let it train. So it's going to take some time for the model to finish training. I think somewhere of the order of 15 minutes or so. So you probably should see the accuracy. I mean, you will see it going up, but it probably would not go too high. In this case, up to say 30%. That's all I got. That was not unexpected. So anyway, I think so. The images, the labels are kind of a bit weird to me, right? And then also we are using about only 500 images per class. So that's quite a small data set actually, to be honest. So I'm not, since MobileNet is trained on like different entities, right? You've trained on tools versus trees versus humans versus different types of animals. So these are all completely different things. So in order to learn the subtleties of emotions, I don't think that is going to get a very good accuracy, at least with a very simplistic model architecture like that. We just added a few layers on top, right? So that's probably going to be the accuracy that you'll be getting, about 30% or so. So I think the model will take some time to run. So maybe before I go on to the next part where we evaluate the model and then do the fine-tuning portion. So maybe should we have a coffee break? Show of hands. Yes? Okay. So let's take a coffee break while the model is training, or tea break, or toilet break, and then we'll come back in about 10 minutes to see the model results. Okay, so let's continue with looking at your model and evaluating the accuracy. So just to recap, what you've just done just now is to do a model.feed, right? And then you basically pass in your training and validation batches. Right, so these are the TF data sets. You pass it into the model, feed it, and then you store it in history. So that's a really useful way for you to evaluate the metrics later. So using the history object, you can basically plot your training and validation accuracy and loss. Right, so the accuracy, as I said, is not that great. So for training, you manage to get about 45% accuracy, and then for validation, you get about maybe 30% accuracy, right? Anybody got more than that? No. Yeah, I don't think so, right? So recognizing images on a whole bunch of like 1,000 different classes, not quite the same as recognizing human emotions. And our data set size is really small, right? So we are going to expect like not a great accuracy, but 30% is okay, right? Maybe like at the level of a little baby, you kind of recognize human emotions with some lesser accuracy. So we have trained for 10 epochs, and then that's what we managed to get. So the model is still learning something, not that great, but okay, that's still okay. So, but now generally when we do transfer learning, there are the next step after you've trained your basic classifier is to do fine tuning. Now, so fine tuning allows you to bump up that accuracy to a little more, usually a few more percent than what you can get with just your basic classifier, which basically is just training on the top layers that you've added, right? The base model is frozen. In fine tuning, if you have a big enough data set, you would want to fine tune and you unfreeze a few more layers at the end, and then you get those weights to be trainable as well. So just a note of caution, you should only do this after you did the basic transfer learning first. So you let the layers recognize the classes first, then you unfreeze the layers, and then you do the fine tuning to let it tune. Otherwise, it's just trying to randomly classify, and and you want to keep, so basically you want to keep that top few layers that's already accustomed to your data set, and then you get propagate down to the next few layers that you're going to unfreeze. Right? So here we are going to unfreeze the whole base model for now. So set base model.trainable equals true. Okay, and then you say that, okay, I'm going to fine tune at 100 layers onwards. So you've seen the base model has got a whole bunch of layers, very long list of layers. We will start from 100 onwards, and then for each layer in base model.layers, you will want to set trainable to false. Okay, so basically you freeze all the layers up to layer 100. It's already unfrozen, and then now you freeze the first 100 layers, right? So from 100 onwards, you are going to get the trainable layers, including your classifying layers that you added on top. So you compile the model again using the same optimizer and loss and metric. Then now the model summary is going to give you a much larger number of trainable parameters. You're going to train on 1.8 million parameters. So these weights are going to be tuned and accustomed to your emotion data set. Okay, so we are going to train our model again, and this time round it's going to train for another 10 more epochs, and it's going to take some more time. So we won't be waiting for, in the interest of time, we won't wait for it to finish running. I'll just show you the results first, and then we can go for lunch, and then you can come back and play around with your model. Right, so after 10 more epochs of fine-tuning, you bump 30% accuracy up to 37% accuracy. So that's okay, a bit better. So this is our metric. So this is the first 10 epochs where it's not where we didn't fine-tune the model. So after that, we start fine-tuning the model, and then you can see that the accuracy goes up just by a little bit. And here, the training actually goes way off, starts to deviate from the validation by a lot. We are getting like 80-90% accuracy on the training data set alone. So apparently it's recognizing emotions very well on the training data set alone, right? So we are totally overfitting the data right here. We have 1.8 million parameters, and we overfit on like 500 images per class, right? So not doing great, but so say if you have a larger data set, then this is something that is worth trying, right, to get that few percent of accuracy on top. If you have huge data set, then you want to first train your model, first do the transfer learning, and then fine tune that later to get more accuracy. So now we are going to do a prediction on our, let's take a look at our predictions. So we have our different emotions. So on our, I'm predicting, so I use the model to make predictions on my test set. And this is the confusion matrix that I got. Apparently 3 is the one that's being classified pretty well. So happy is a pretty recognizable emotion by the model. The rest of the emotions are not doing too great, especially disgust. So disgust is probably quite difficult to recognize. Maybe it's representative of how humans look at things too. I don't know. Might be not so easy to recognize. But happy is definitely one of the first things that you recognize, right? And I know as a new father that the baby recognizes your happiness very quickly. You smile at the baby, and then he's pretty quickly he starts to smile back at you. Other things not so quick, right? So now then for the other, let's say 5 set, you see a whole bunch here, right? So many other emotions get somehow mapped into a set emotion, right? So you can see that in the our sample that we're going to try out. So this might be fun for you to play with later on after you've trained your model. So you can basically go on the web, download a bunch of facial expression images or a bunch of faces, upload it to the sample image path folder here, right? So if you go into sample images, I've got a bunch of sample images for you to test on. You can upload your image just by clicking on this button here. So upload your image that you download from the web, and then you run this segment here, which will unpack all your images into a list and then do a transformation. So here are my sample images. So I got from the web. So this is Pablo Escobar, I think. I've even gotten a cat here. So a cat. This is a Jack human, right? Hugh Jackman. And then I have a Mona Lisa and then the grumpy cat. Right? So let's see what the model recognizes. So it does its predictions, and then I'm getting happy, neutral, sad. So sad is, as I said, many emotions somehow get mapped to sad, right? But I've got the first 2, happy and neutral. happy is okay. Happy is good. Sad, not quite, but it's a cat. So I this is. So I've got on one of my training runs, it managed to recognize this as angry. So I thought that was pretty interesting. So the model is able to predict on a different emotions on different species as well. And then Hugh Jackmantle, this is sad, supposed to be sad, which under some circumstances might be sad, right? I mean, it could be a very, desperate cry or something, right? So it also depends on how your labeled data set is like. And then you've got sad here, and then Mona Lisa is sad, Grumpy Cat is sad. Right, so that's something you can play with after your model is trained. So this is the next part that we've been talking about. So you can save your model file after you finish training it. You just do a tf.saved model.save. That will basically just save your model into this saves it into a .pb file. And you can also do a model.save and just save into a HDF5 model format. And then for the purpose of devices, you can do a conversion from your, let's say my emotion.h5 file, and then I do a tf-like convert in command line and just save it to, convert it to output tf-like file. So this is going to be used, can be used for serving on devices. But this is also exactly the part where I said that for TF2 and this TF-like convert part, the things are still not worked out yet. At the moment, this would probably work well on TF 1.13. But if you're using TF2, this would probably not work on your devices. So you can try to repeat the whole thing again in 1.13. Maybe you have to modify a bit of the way that you do your model building. And then you convert the file, then this should be able to work on your device. Right, so here you can do a conversion, load it to your device, and then do prediction. Right, so basically, in summary, we have done transfer learning. So transfer learning, you have basically two stages. First stage, you freeze everything in your base model, add a few top layers, classify, just to get the top layers accustomed to your fine-tuned data set. And then you fine-tune that later by unfreezing a few more layers, and then get the model to bump up the accuracy a few more %. Right? So there's the two stages of transfer learning. Word of caution, if you have a small data set, then you would almost definitely overfeed. But the model seems to also be able to generalize to maybe other images. So it'll be fun to see what you guys try on the model later. And then, yeah, so if you want to serve on your device, 1.13 is the way to go for now, but 2.0, well, we hope in a few more months that it will be compatible, and then you can load the model TF-like into your devices. So the challenge for you guys is probably to try out on different images and see if you are able to get better accuracy than 37% by maybe adding some more layers and having more complicated architectures on top of the base model, right? So you can totally try to add a few more things and see whether you can get much better accuracy. So that's the end of the modeling workshop. Any questions?